Bjorn. I'm a principal engineer at Qualcomm. So I've been dabbling with the Linux kernel on Qualcomm hardware, or on hardware based on Qualcomm SoCs for the last 16 years, and been playing in the upstream community for 11 of those. Co-maintaining the Qualcomm SoC and the remote proc subsystem, and I've been dog fooding the upstream kernel on laptops with a Snapdragon processor since 2019 with C630. And after several years of various out of 3 ways of running my kernel, as of 6.5 or maybe 6.6, definitely 6.6, I was able to send a couple of patches to the Arch project, and since then I'm actually running the kernel that Arch Linux ARM is providing. So the development model when it comes to the kernel. So development and testing happens on a lot of different kernel branches. We have Torvalds master branch, the various releases thereof. We have Linux Next, and we have a multitude of integration branches, both kernel org things and, for example, the Linaro integration branches. What's common between all those is that they're all moving baselines. So they're updated by other people all the time. And as a developer, we often need to jump between multiple ones of these. We get bug reports on some RC kernel, and we do feature development on Linux Next and so on. So a lot of jumping in between those. So that means as a kernel developer, we need a kernel-centric development model. And we want things like reduced compile time, and we want as much of those tools around how we work with the kernel to be standard. And those same things goes for if you work on some sort of component in userspace or around somewhere else in the platform, that you want a development model that is centric around your component and cut out all other parts. And this is different than from how you would, for example, develop a software platform that you intend to release in whole to someone else, for someone else to consume it. Here we're talking about how do you efficiently develop your component. So the way we used to do kernel development for many years in the Qualcomm upstream community is that we use some form of RAM disk for our testing. So the kernel is built using the standard K-build and make mechanisms. Many people have some sort of convenience wrappers around that, but it's based on pretty straightforward. It's pretty much the kernel build system straight off. The RAM disk, it's a compressed CPI archive. So what that gives us is that by nature we can concatenate multiple such CPI archives and stitch together things, which means that we can have a pre-built RAM disk with some sort of test user space, and then we can supply artifacts from the kernel, and we can multiple of those, and we can stitch them together. And we stitch that together into a single package that we want to test or try out, and we can either do that as an Android boot image, which is traditionally what we've used on the Qualcomm platforms due to the Android bootloader, or the UKI, which is sort of packing the same information, but in an EFI application. And that's a new thing that's coming in the newer targets, or have come in the newer targets. This single encapsulated image containing kernel and your test environment, it's very suitable for fast boot, where you have this thing and you push it to the device at boot time, and yeah, this gives you a very rapid development cycle because you rebuild your kernel typically incrementally and just stitch things together. You don't rebuild anything unnecessarily. But as your scope grows, this model has some limitations. So what we then have used to do is that we turn to some sort of full distribution testing. So when your RAM disk isn't enough, you have outgrown your build route, you turn to Yocto, you outgrow Yocto, or for some reason, your test image is just too big. You can't fit all of your test content in RAM, for example, or you don't want that big of a RAM disk. Or just that you get bug reports from someone running your component in a full distro and they need some help debugging something. So we have had different ways to how you actually install a full distro on your development board. Typically, they are it requires a bunch of manual steps, or it's a specific release for a specific board, and you lose the flexibility of our workflow that we had. The distro installers is very limited in that typically you either need to have your device already out there so that it's made its way into the distro, or you need to do a custom thing. And typically results in some manual steps. I mean, it is straightforward if you know how to do it, but it's not efficient. So if you can actually get your Linux distribution onto your board, the way you typically would do it is you do some sort of cross-compile of your kernel on your faster machine. You copy your artifacts onto the dev board, and then you install them either by using some distro mechanism for installing your kernel, or simply copying files in the correct place for where your manually set up grub config or something like that points to them. So this is how we did it for many years. And the problem is that when someone asks you, how can I reproduce that on my board, or how do I get started on my new board, that's always complicating. So enter MKOSI. So part of the systemd project, there is a tool called MKOSI. It's effectively a wrapper around a whole bunch of different distro installers. So it supports all the different distributions that we tend to care about, and some. It's used by systemd for composing test systems. So when they get a bug on some particular version of systemd, they can use MKOSI to generate a OS image or a container image with that specific version, and then boot that, typically in some sort of container or a VM for testing. But conveniently for us, it supports multiple different output formats. And most interesting for us, I think, is the disk output. And in the default configuration, when you say disk, MKOSI will spit out an image which contains a GPT partition header, EFI system partition, and a root file system. So that looks like exactly what we would like to have. You can configure it either through for command line or configuration files. You can say, should this be a bootable image or a container image, and so on. And you can specify what packages do I want in my installed system or in my image. And since a couple of months ago, you have the ability to say, if my system is bootable, I want the boot or the OS loader to inject this particular device tree blob as I want as well. So we don't need UFI support for selecting device tree to use this on our development boards. And also it supports cross-building, so you can work on an x86 64 machine and generate an ARM64 image. And next slide, please. So the configuration, it's split in a few different sections. You can see an example here on the right. You have a distribution section where you specify what distribution do you want in your image. Those that I've played with are Arch Linux, Debian, Fedora, and Ubuntu. You can specify which distro version you want and which target architecture. In the output section, so we had the disk output. There is also an option to generate a CPI archive or a UKI file. And I think you can generate, for example, a directory, so you just get all the system installed in a directory if you want to do some post-processing and things like that. In the content section, you select whether the thing should be bootable, and if so, which bootloader do you want? Do you want systemd boot or grub? You can specify your kernel command line, your device tree override, if you want one of those, if your UEFI doesn't provide one. You specify your root password and host name of the image, and which packages from the distro that you want to have installed. And next slide, please. Thanks. So this allows us to take a distro, take a version of a distro, and generate a disk image by some set of packages. But for this to be really useful for us, we of course need to bring our own content. The kernel build system today, you can use make a bin-deb package, bin-rpm package, or pacman package as your make targets in the upstream kernel, and out comes the deb or rpm or whatever arch package files are named. And so you get those files, and typically you can move those to your distribution or your system and install them using your distro tools. But MKOSI allow us to specify a package directory where we say, here is additional packages, and we can throw our upstream built kernel package into this directory. So this allows us to customize or to bring our own kernel into MKOSI. In the same way, so with runtime firmware, unfortunately not all the boards we have are supported in Linux firmware. We have runtime firmware that you need to bring from the side. There is a directory where you can stash files, which will be automatically just inserted into your disk image. So the MKOSI extra directory, it's effectively just an overlay. So add your firmware files there. And it also supports some level of, or it supports building pieces from source. So you can say, set up my image and then build this userspace component, for example. So you can use it for development and testing of, or that's one of the things that the systemd project is using it for. Next slide, please. Thanks. So with all these options and things, I created the MKOSI QCOM project, where I have placed a bunch of convenient base configuration and some documentation of how to do these things. So with this project, you can effectively run MKOSI-D and specify which distro you want. You can specify a device tree if you want one. Otherwise, you will have to rely on UEFI providing with you one. You have some profile support, and then you build. And when this then run, it will take a little while, and out comes an image.raw, which is sized according to whatever options you choose for your system. And the profile thing, the main thing there is that as this generates a raw disk image, the standard, without any settings, you will get the sector size of that image of 512 bytes. But for our UFS devices, that has to be 4 kilobytes. So there is a profile for selecting UFS, and then that effectively only changes the sector size. So the image will be either NVMe or UFS compatible. So this image, we now have our GPT, E5 system partition, and root file system. So we can burn that straight into NVMe or the first UFS LUN. And then on the user disk, so to say, we now have a full Linux installation. So we can do that with for example, QDL. We turn on power. We are, after a while, greeted with a login prompt. And just log in with root, and the default password is 14. That should be secure enough. You can find these configurations and the documentation, the steps on the Qualcomm /MKOSI QCOM project on GitHub. So what if we want UI in our image? Because this is typically one of those major steps between what you can do in your RAM disk and when you need more to test and when you outgrow your RAM disk. So effectively, you need to make sure that your GPU firmware is available in the either in a Linux firmware package or in that override or MKSI extra directory. And then you need to add relevant packages to your list of packages. So for Debian, effectively, you just say, I want task GNOME desktop. And then you rerun MKSI, and out comes a larger image, a much larger image. But yeah, when you boot that, and when you install GNOME, it will go straight into GDM, which doesn't allow you to log in as root. So it's so you have to either you have to use UART to create a user, or you can use post-install scripts in MKSI to, inside the container during installation, you can create the users. I don't remember if I kept that in the project or not, but yeah, let me know if anyone wants that, wants the scripts for that. So next slide, please. So this is the outcome. So here we have the same setup. I ran on the left. I said I want a Debian system for the X1E CRD, and then I used QDL to put that on NVMe. And in the right picture, from the same directory I ran. I said I want the RB3 Gen 2 device tree instead, and I want the UFS profile. Well, it's a special one for RB3 Gen 2, but it's effectively the UFS profile. And out came an image that I could just burn to the UFS. And I have my fully working GNOME environment on running out of the box. So some tricks when it comes to MKSI. So it depends on the systemd in the host operating system, and it depends on some modern features because it's from the systemd developers. So there is a feature called tools tree where MKSI would first build a modern host OS for you with new enough systemd so that it can then build the actual image that you want on your device. So that's disabled as default in the scripts, but it's just commented out. There is another output format, the CPIO, that gives us the ability to effectively just build a pre-built RAM disk. So the same thing that we used to use Buildroot or Yocto for, we can use MKSI, and out comes a 10 times larger RAM disk. We can do the same thing with UKI, and this is how I've been installing my laptops since I got this up and running, where I generate a UKI-packed Arch OS with the Arch install scripts package. So then I boot that off a USB stick, and when that system is booted, I can then follow the Arch installation guide to get my system onto the actual storage device. Yeah, so it's effectively there you can, and before the distro supports your hardware, you can add your custom kernel, and you can throw that same kernel package into the extra directory. So when it has booted, you have that kernel, so you can just pacman-u, I think it is, to install it. So everything works right. Well, so systemd boot doesn't uncompress image.gc files. Debian has solved this by in the package generation step, they actually package the VM Linux file and claim that that is the image file. So there it, yeah, you can see it from the outside, but there it just magically works. Fedora, they're shipping the compressed image, so you can't actually boot boot Fedora with the upstream package or with the Fedora kernel package without unpacking that. The Alarm Linux ARch64 package, well, MKSI doesn't consider that to be a valid kernel package, so you can't choose the Arch kernel package, but you can build your own Linux upstream package and override that with. And then there is the fact that when you do make any of these package outputs in the kernel, you will typically get the image.gc file, so I sent a patch to try to change that to match what Debian and Arch does, but yeah, I haven't gotten that. It wasn't well received at first, and then I haven't gotten much feedback. So for now, you have to enable the zboot flag, which package up the compressed kernel with its own unpacker. One other problem is the fact that the kernel config is maintained per distribution, so we need to enable our hardware in every distribution. There is no automatic method for selecting kernel modules that you probably need for your board. So today typically you can say, I want all the modules, and that generally works, except if you run out of storage in your EFI system partition. On Alarm, you have the thing where if you run on an x86 machine, the x86 version of Arch doesn't have the key ring files or the key ring package for the ARch64. So you can't install any packets. So you need to install the key rings on your host machine first. And of course, the MKOSI depends on the fact that you have a UEFI boot flow. Okay, so device tree selection, proper solution would be for UEFI to provide device tree to us. Well, MKOSI has this ability where you can now specify a device tree, which will be used instead. So that works for us. But if you generate an image and then install a kernel packet, then that will not adhere to the same override mechanism. So there is a manual step that you need to make sure that you, on that second boot, would actually get your right device tree, or the correct device tree loaded. And then we have the usual problems of you have to remember your clock ignore unused and PD ignore unused. There is work going on trying to handle or to be able to boot the kernel without those. But that, as for now, you're still gonna need those. And then we have some interesting things like on the RB3 Gen 2, I had that profile which wasn't UFS. That's because CPU frequency scaling is depending on the driver, which is in the RAM disk. And if you give it like 500 meg RAM disk, then it takes longer time to unpack that RAM disk than what the kernel will wait before it determines that the probe deferrals didn't complete in time. So then you have a semi-functional system at best. So you need to extend that. There is that deferred probe timeout, which we can extend as a workaround for that for now. And then, yeah.
You need to point MKOSI to a pre-built kernel, or let it go to a
So the question is if we need to specify a pre-built kernel or not. So if you don't specify anything, it will pull the kernel from the distro. And then you can specify it if you want your own functionality or your own, yeah.
So what happens to real-time caching and other things that you use to optimize?
So in the case where you pull the binary from, say, Debian, I mean, then it's cached in binary form. In the case where you want to bring your own kernel, the kernel you build is built in a kernel-centric way. So it would be up to you to use Zcash or something, or a fast machine, or however you want to generate that image. One of the interesting problems that we have is the fact that if we put kernel modules in the RAM disk and the firmware isn't there, several of our device drivers will determine that there is no firmware and will not retry once we have a root file system. So some generic problems. Next slide, please. So what about the Android bootloader? Because all this depended on UEFI. And most of our development boards out there, they're built on ABL. So ABL, it loads the kernel, RAM disk, and device tree from a boot partition and then just jumps to the kernel. It requires a custom packaging step, and it has some drawbacks for us developers, like there is no kernel selection mechanism. If you get your command line wrong, then you have to rebuild the image and so on. So it works good for embedded products, but not necessarily for developers. But Fastboot Boot provides a really nice test cycle, test loop for us. So the project ABL to ESP. So one of the problems here is that we want to bridge between ABL and that UEFI environment in order to run our UEFI applications, like system deboot. So we have this, or I wrote this custom minimal re-implementation of ABL. Effectively what it does is it's a UEFI application, connects all the drivers, searches all storage for a boot AA64, and if it finds one file with that file name, it just tries to load it. So this allows us on many of the development boards that is based on ABL, on the ABL boot flow, to bridge into EFI system partition. And we can run systemd boot, for example, with that. And this is for engineering purpose only. It's for the cases where we have development boards out there that is based on the Android bootloader scheme, where we would like to, for convenience sake, bridge to an EFI world. And you can find the project at Qualcomm/ABL2ESP. But I miss my fastboot boot, in particular on all the Windows devices. We don't have fastboot boot. Because it's more a standard EFI application or a standard EFI system than the Android way. But for boot automation or for our rapid development, we will really like fastboot boot. So for that, we have fastboot.efi, which is a minimal re-implementation of the parts of ABL that does the fastboot stuff, or it implements the device side of the fastboot support. So it's a standalone EFI application written using the UEFI Rust crate. And if you do EFI application development, I highly recommend looking into that. It can be dropped in either as a boot AA64 EFI, or it can be chain loaded from systemd boot or grub. It supports to boot Android boot images, so it will be transparent to what we're used to, except that it doesn't uncompress the kernel at this time, so you have to give it the image. Or it can detect that you fed it an EFI application, and then it would just load that EFI application instead. So you can effectively fastboot boot chain load something else. And it has removed all those artificial image size restrictions that we find in the ABL that we actually ship. So for development, this is perfect. You can, if you have a newly provisioned system with all the non-Linux side flashed, what I do is I use systemd repart to generate an NVMe image or a UFS image containing fastboot EFI as my boot AA64, and then I just flash that at sector 0 and forward on my device. And when I power on, it goes straight into fastboot. So that allows me to get from 0 to a fastboot boot system in seconds. And the code is available there as well. And here are the various links throughout the presentation. Thank you. And that says 0, but I don't know if we have time for any questions, or do we have any questions? Crystal clear. Good, thank you.